Welcome back to another class on speech signal processing. Today, just to refresh what we were doing, we saw quite a few different architectures. One of them is called the deep feed-forward neural network, which went only from in one direction, right? So there were many hidden layers, an input layer and an output layer. Then we said for many applications, it's good to have some history, good to know what happened before it. And so we, for example, in language modeling, given some previous 3 words, can I predict what the next word is? So that was another kind of architecture we looked at, which is called the recurrent neural network, where there is a feedback, so that from the hidden layer of the so now we are progressing along time, and so each input is like one time instant. So for the next time instant, the previous input's hidden layer is fed again as an input at the second time instant, and that is called the recurrent neural network, and that keeps track of history and good for sequence problems, where the order in which things occur are very important. For example, in language, right, the order in which I produce the words are very important, right. So today we are going to look at a different kind of an architecture, which is called convolutional neural networks, and these are generally used or used to be very popular in image processing, okay. But we will see now that it's also extensively used in speech and other domains also, NLP and many other domains, okay. So what is this convolution? I mean, so we have dealt with this somewhere in the past, but I'll remind you. So this is in the first few lectures of this course. I was talking about signal processing concepts, and so there was this concept of convolution that we had discussed. I'll remind you what it was. So we are talking about systems, right? So these are systems. A system is nothing that takes an input. Normally we take discrete samples, so that is the input, and manipulates this input to give some other output, right. So it can be useful, right, in many applications. If I am removing noise or doing something, it might be useful. Sometimes nature itself is a system, right. So when I am speaking and it is going across, and then you can see some background noise, that is also a system, but now it is corrupting the signal. So that is something that we cannot control because nature, right. So system is something that manipulates input and gives an output signal, okay. There are a class of systems that are very important, which are called linear and time invariant, right. And we have talked about it, so I am revising it, but if you go back to your lectures, you will see that I have talked about such kind of systems. These are satisfy some properties called linearity, that is, if I add 2 signals, the output should be the addition of the respective outputs, and time invariance means if I delay the signal, the output also should be delayed by the same amount, right. So if you have a linear time invariant system, the beauty of the system is if I feed what is called an impulse, okay. So again, if you have forgotten all of this, this is something that you can look up in the previous beginning lecture, and you will get an output, right. So this is a system which we are assuming is LTI, and this is the response of the system to the impulse. So this is called the impulse response. And if you have forgotten, this is basically some kind of a impulse means something that occurs for a short period of time. So so -1, -2. So basically I give some kind of a short energy boost or something like a signal, and the output is looking like this. I measure this output. This is a one time effort. Then you give me any arbitrary input, any arbitrary sequence, right. So I have I sample the signal, so I get some arbitrary input which I call x of n, and if I feed through the system, okay, we know that the impulse response of the system is h of n, then I can tell you exactly the output, okay. That is amazing, right. So what am I saying? You give me any arbitrary input, I give x of n, I can tell you exactly what the output y of n is, provided I know h of n, okay. And that is given by something called the convolution sum, okay. So this symbol means convolution, okay. what does this do mathematically? I will come to it. So, this is nothing but x. So, there is a variable, some other variable that I have to take, because I am going to sum it out, and then there is a dependence on n, and the relationship is like this. So, this is a mathematical idea of convolution. So, like how addition a plus b, 1 plus 2, subtraction a minus b, right. So, 3 minus 4 minus 3, whatever you want, right. Similarly, this is a mathematical operation. It takes two operators and does some operation like this. Okay. And in practice, we do not have delta. So, we give a very short, I mean, give some kind of a pulse like this, and it is sent across a channel, and then I measure it, and if I assume this channel is linear and time invariant, then it is enough to find out the output for any given input by using this mathematical relationship. This is called convolution sum. Remember, I am going to be talking about convolutional neural networks that is used in image processing and so on and so on. So, what is the relationship? We will come to this. Okay. So, this is something that you would have heard in the beginning few lectures. Then there is also a concept of filtering that I had discussed also in the beginning few lectures. So, what is filtering? Filtering means removing some parts and retaining some parts, right. I filter, right. So, if you have coffee, a powder or something, you put it and then you put water and it filters out and only the liquid comes out, what is called the decoction, right. So, how do you do that? So, there are many practical uses of filtering, right. So, for example, if I had a smooth signal like this, right. So, nice smooth signal, right. Okay. And then I have some noise signal. Let us say that I have some noisy signal like this. Okay. So, noise is something that is unwanted, right. So, you want to get rid of noise. Okay. Now, if I have the signal, but because noise is something I cannot control, it is coming from nature or something. So, this noise is there like this. So, my actual x of t will look like this, right. It is going to look, because I am adding the noise signal on top of the speech some signal, right, and this is my actual signal. But I want to get rid of noise, right. Noise is something that I am not interested, right. So, what can I do? How will I get rid of it? So, let us say now I am talking about a system, which is I am talking about, I will again go to discrete, but you can understand the relationship between discrete and continuous. So, I have a system which is a cleaning system, and let me assume it is LTI, okay, for some reason, and I give y of n equals 1 by m summation m or 2m plus 1, I will come to why it comes, m equals minus m to capital M x of n minus m. Okay. If I do something like this, what is it doing? So, if I am looking at the 5th sample y of 10, right, or 10th sample, so here n is 10, okay, and let us say capital M is 2. Okay. So, I am going to take capital M equal to 2. This is 1 into 2 into 2, this is capital M plus 1 summation m equals minus 2 to plus 2 x of what is now 10 minus m, right. So, this is equal to 1 by 5. When minus 2 is there, 10 minus of minus 2 is 14, and when it is plus 2, it is 8. So, it starts from x of 8 plus x of 9 plus, when m is 0, then x of 10 will come. When m is minus 1, it becomes x of 11, and when x is minus 2, it becomes minus of minus 2, 10 minus of minus 2 is plus 2, right. So, there are 5, how many samples are there? So, 3 plus 2, 5 samples. So, this is the average around x of 10. I am looking at 2 samples before it, 2 samples after it, and x 10, and I am averaging it, right. If I do something like this, okay, this is called a smoothing operation. You will see, because if what will happen is the y of n will look somewhat like this. So, remember how was S of n? S of n was a nice smooth signal. Then I had noise added which made it fluctuating. So, I actually get x of t, but let us say I did some sampling and I am actually in the discrete time domain, because it is easier for me to show summation. I can do integration for y of t if you want, okay. And basically what it's trying to do is it's smoothing out all these ripples, and this is a smoothing operation. So, this averaging or smoothing operation it is called, okay. So, and why is it working? Why is it able to smooth out? And you can see. So, if I take an n of t, right, if I take n of t, there are plus and minus quantities that are happening, right. So, when I do some averaging, that it averages to 0. So, after passing it through this smoothing operation, n of t becomes almost 0, okay. But this s of t, which was originally like this, by smoothing operation it is going to get piecewise smooth kind of thing, and so still it will capture the smooth structure. So, it will become smooth even when I do smoothing operation, okay. Depends on how much I am smoothing, but nevertheless it will almost maintain the shape by fitting a piecewise linear kind of a curve, right. So, when I add these two, and that is what the filter is trying to do, the noise is getting rid, but the signal is being preserved as it is, okay. So, it does not change much, and that is why you get back the original signal. This is usually what is called low pass filter, and so this is exactly what a convolution operation is actually. So, I introduced two ideas to you. One idea was something called convolution, which is very important for linear time invariant systems. In traditional conventional signal processing, we use it a lot, and that is useful because given an LTI system, if I know the impulse response, the output for any arbitrary input is given by the convolution sum. So, I can find it mathematically without even feeding it through the system. The other aspect that I talked about, and these two are related, is the aspect of filtering. Filtering is where you want to get rid, or you want to do something useful, and therefore, you might want to smooth out and remove the noise part of it and make it clean, and you get back the original signal, okay. So, these two are very important concept.